Hey everyone, today we're going to be talking about graphs. If you haven't already, please watch the prerequisites so you're familiar with some of this graph terminology, and because I'm going to kind of jump right into it. All right, so let's talk about some graph basics. I'm going to be using a package today called NetworkX, and it's in Python, and I'm going to have some instructions in the next lecture on how to install it if you haven't installed it already. So don't worry about that quite yet, but you can see that I'm importing it, and the only other thing I'm doing here is matplotlib. Okay, so you can see I've instantiated a new graph, and I'm going to call it G. And I'm going to add some nodes to that graph. And to do that, all you do is you say G add node, and then the node name. And it could be a number, a letter, a word, however you want to name it. You can name your nodes whatever you want. So then, once you have a few nodes defined, I've defined A through H. You can just use nx.draw and then on the graph object, and it will draw you a picture of your graph. Now you see that this is just a bunch of nodes just kind of hanging out. I don't really have any edges yet, so let's go ahead and define some edges. And so here I've defined edges, and I've said I want there to be an edge between A and C, an edge between B and C, and so forth, so on. You get the idea. All right, so before I draw it again, I need to define a layout, otherwise this isn't going to be very pretty to look at. So I'm going to use the spring layout. Graph layouts are kind of funny. I'm not going to talk about them a whole lot, but basically you could spend a lot of time playing artist with your graph. All of this is documented on the NetworkX documentation, the website, if you care to play around with it. If you don't, if you're not much of an artist like me, then probably the best thing to do is to always just use the spring layout. And spring layout is going to lay out your graph in kind of a random way, but it'll hopefully be a good way. And if not, you can just run your display a few times over again. So you can see I have a graph displayed here, and here I've labeled my nodes as well. And what you can do is, if you don't like this particular layout, you can run it again, and you'll get another layout. You can run it again. You get a different layout every time. Now, keep in mind, these graphs are all the same. So this graph, even though the layout changes, all of the nodes are connected to the same nodes in the right way. So each one of these graphs, the terminology that we use here is isomorphic. So each of these graphs are isomorphic with one another. All right, so now that we have our graph laid out, I'm going to show you this thing called centrality. And what centrality is it's a measure of how important or central one of these nodes is to the graph. All right, and so to do that, all you do is you call nx.eigenvector centrality underscore numpy on the graph object. And what that does is it gives you back a dictionary of the node and its centrality score. Now, what you need to know about this is that a higher centrality score means that the node is more important to the graph. So you can see here that like C and D are very important to the graph. And that's not surprising because look, C connects these two to the rest of the graph, and D connects all of these to the rest of the graph. So without C or D, the graph would really fall apart. A lot of nodes couldn't connect to each other. And that's kind of the basics of what centrality is. Now, the one I've used here, eigenvector centrality, there's a bunch of centrality measures. So eigenvector centrality is one of them. Betweenness is another. PageRank is another one I'll talk about in a second. But the important thing is that there's a lot of different metrics that you can use to measure centrality. They're all slightly different. So how the one you choose probably depends on the exact job that you're doing. But let's look a little bit deeper at how eigenvalue centrality looks. So what I've done here is I've made some just some quick code that's going to put the eigenvalue centrality numbers on their respective nodes. So this graph is still isomorphic to this one. And you can see that we have a couple of really important nodes here, C and D. And these very important nodes are the nodes that are responsible for kind of tying the nodes together the most. So you can see that 0.12 here on this node isn't so important because if he wasn't connected, no one would know except for him. This one here is a little more important because he's responsible for connecting this one. This one here is more important still because it's responsible for connecting these two. This one here, now it holds up 4 nodes, so its eigenvalue centrality is a little bit higher still. Okay, but so what? How would you use this? Here's a few ideas. So the first one, and the one that we're going to talk about the most, is let's say that we're trying to find an influential or popular or important person in a social network. Someone that we really, that's really influential and important in a group of people. That would be a really good use case for this. We would look at eigenvalue centrality of each person. Eigenvector centrality of each person, and then we would find the one that's the most, that has the largest eigenvector centrality number, and then we would know that that person is probably the most influential in the social network. I linked in this article that you're welcome to read if you want. It's about how Facebook's been used in elections previously, and actually how Facebook has changed recently their Graph API so that this kind of information isn't as available as it used to be. Okay, so that makes sense. What about some other ideas? Let's say that you have very limited funds for some place like a hospital, and you want to spend that money wisely, improving each room or each area in the hospital so that these improvements cause or help prevent infection. Or the use case I saw in particular was about MRSA, and they wanted to reduce the spread of MRSA. And so what they did was they used eigenvector centrality to find the rooms or the areas in the hospital that have the most patients in them, because those are the places where the risk of infection are highest. Just some other ideas. Let's say you need to place a food stand in the optimal place in an airport. The node in the airport where the room, the area, the hallway where it has the highest eigenvector centrality is probably a good place to put your food cart. Lastly, let's say that these were websites and you wanted to build a search engine so that it referred you first to the pages that were most linked to. PageRank is Google's famous centrality measure, and that's a graph centrality measure as well. Another one I didn't point out, but consider it number 5 on the list. Let's say these were computers in a computer network, or more specifically, they'd probably be like routers or switches. You could figure out which ones do you want to have the most redundancy for, or back up the most, or the ones that are the most important, and so that need to be protected the most. Okay, so that's the idea of graph centrality and why it's so important. I'm going to give you a short use case next that shows you one way that we could use it. Thanks, bye.